All right, I guess we're live. So I was last night listening to. Going to be a little bit off topic today, but I think the topic is important. I was listening last night to a really nice documentary, very professionally done about chaos. And I wish I had the title in front of me. Jim Al-Khalili did something. It was a series, and it was just on YouTube, so I watched it, and it really got me thinking. What he was talking about was chaos. And I've mentioned chaos on this channel a few times, but not recently. So I think it's good to revisit this topic once in a while, kind of as an explainer. All right. And one of the things I took away from his explanation of the documentary was that up until about the 1960s and 70s, the relationship of science to chaos was antagonistic. Scientists, if they found unpredictable results in their data, meaning the exact same experiment when done over and over and over, produced non-repeatable results, meaning that's what they saw, that they couldn't repeat their results. They do the same experiment, they couldn't repeat their results over and over and over. And that looked chaotic or non-repeatable. And in science, if you or your peers, which is even worse, if you or your peers cannot actually repeat your work and get the same results each time, mix this with that and you get a solid, or you get flames, or you get smoke, whatever. Okay, if you can't do the same experiment over and over and get the same or very, very similar results, then it's just not good science. It's actually not good science. And there was this antagonistic relationship with chaos in the sciences. And in his documentary, he pointed that out again, and he was very forceful about that. Really the first half, almost the entire documentary was about the antagonistic relationship that science had with chaos. Because there was this perception that you couldn't do good science. And part of this even goes back to Isaac Newton, right? The great, one of the three most influential scientific thinkers on the planet's history of humans ever, right? So Isaac Newton, justifiably a brilliant man, did some many, many brilliant things. But he also, it was a long time ago, he was a devout Christian, and he had very clear views on how the world operated. And a lot of that, like it or not, was based on Christianity. That the world was created. It took 6 days, and so on and so forth. That the world was deterministic. You see? Deterministic. It had a beginning, it had an ending, and that this was God's will. I mean, that's how people used to think. They were doing science with that mindset. And so Isaac Newton, a brilliant man, doing science, okay, nevertheless had a very narrow focus on what he really expected from his work. He already had an expectation that if you measure this and you measure that and you do something else, the results will be repeatable. Now, in fact, there were aspects of his work with doing planetary orbits, and he was looking at Venus and Mars and Mercury, and even his own work and the work of people that came after him noticed that there was a discrepancy with regards to Mercury, that you could do the experiments, do the measurements, make the calculations, do the prediction based on the math, and you get the wrong answer. It would work for the Earth, it would work for Venus, it would work for other, whatever, but it wouldn't work for Mercury. The calculations didn't work. And a lot of people, they didn't know what to make of that, but they didn't like it. And they just kind of ignored it. It must be wrong. We're doing something wrong, whatever. Albert Einstein came along and says, I can tell you exactly why that's happening. And, he explained it using his theories and observations, expectations regarding relativity. And by golly, all of a sudden, Mercury's orbit was calculatable to, again, 7 decimal places. I don't mean to say that Isaac Newton was a dummy. He wasn't. But if he didn't like the results, if the results didn't fit his description and expectations for the world, then he was quite prepared to throw them out as anomalous. And scientists have always done that. It takes a very rare person. It's almost like a personality flaw. It takes a very rare personality type to go at science and accept, or at least consider, anomalous results. A lot of times scientists just throw them out. And they'll say, well, I guess we're at the limits of our understanding. Or, well, I guess there was something about the experiment that was just a little bit off. Once in a while, you'll get someone like Albert Einstein who comes along and says, oh, yeah, actually, that makes a lot of sense. And people are like, what? What do you mean it makes a lot of sense? It makes no sense at all. It doesn't follow Newton's equations. Well, Newton's equations are wrong then. Let's fix them. And that's a very rare mindset. That's extremely rare. That kind of attitude is a career-terminating move. If you start saying things like that, we'll have to fix Newton's equations then, because they're clearly wrong, because they don't apply to Mercury. So they're wrong, because there's Mercury. It's part of the solar system. It's not going anywhere. And there it is. So there's your data. There's your observations. And Newton's equations must be wrong. Let's find better ones. And they did. And now Mercury's orbit fits perfectly well with the modified equations modified by Albert Einstein. That doesn't happen very often. That's a big paradigm shift. That doesn't happen very often. Quantum mechanics. The observations around quantum mechanics are based on similar things. There's now a big kerfuffle in cosmology about dark energy and dark matter. They're really concerned about that. It doesn't fit. Where is it? What is it? Clearly something is wrong. The orbits of stars around the centers of galaxies are completely fucked. And they just can't figure it out. It's like, what is this about? How is this happening? How is this possible? We have Newtonian dynamics. That doesn't fit. We have Einsteinian modifications to Newtonian dynamics. That doesn't fit. Is there something? Is the third something we have to find out? And they're calling it dark matter because they don't know what it is. And they're racing ahead trying to find this third path. They don't even know what it's going to be. They're even talking about having to modify Newtonian dynamics, having to modify Einstein's modification to Newtonian dynamics. It's completely unhinged right now. But we've learned the hard way that if you see something that's truly anomalous, you don't just sweep it under the rug and say, well, that didn't fit, so I guess it's not true. Or I made a mistake. Or we're all making the same mistake. We don't do that anymore. And in the 60s and the 70s, we discovered something that had always been there. Always been there. And what we discovered was chaos. We discovered chaos. This one. There we go. What we discovered is that nature, and in particular biology, but nature as a whole, has a lot of embedded chaos. Newtonian dynamics worked even without relativistic corrections. In part because these were, large masses embedded in space, few interactions. But even Newton noticed a thing called the three-body problem. And the three-body problem really, really messes up even orbital dynamics. The three-body problem, which has been popularized in novels, and I think there's a Netflix series even given that same name, the three-body problem, means that whereas you can calculate the orbits of two bodies, one around the other, or two around each other, while you can calculate that, you cannot calculate. There is no solution. It's been tried. There is no solution to three bodies in mutual interaction in orbit. And a typical three-body system would be the Earth, the Moon, and the Sun. The Moon orbits around the Earth orbits around the Sun, and the Earth and the Moon as a pair orbit around the Sun. And that's a three-body problem. And it is chaotic. Three-body problems have no solution. Have no easy solution. Now, that doesn't mean they cannot be predicted, but they have to be predicted using models which run in computers. So you set up your three-body problem, and then you use an incrementing counter to run it forward in time. So here's day one, here's day two, here's day three. Here's what the three bodies are doing. So you can model a three-body problem, and that's how we get to, rockets on the moon and rockets to Mars and rockets to Jupiter. We model these things, and then we still have to make course corrections periodically because the models, have finite accuracy, and so we don't solve the problem of a three-body problem. We model it using computers, and that's the key. You can work with chaos in nature like a three-body problem. You can work with it, but you can't really understand it. It has no solution. It has no solution. You can model it, but you never understand it. Now, the reason I'm bringing this up is because of exactly that statement applies to the Earth dynamic system and global heating and the resulting climate change, all right? That you can model it, but you can never understand it. Your model is limited by how much data you have and how long you've trained the model and how much experience you have using it. But even if your model is very good, you'll never understand the system because it's essentially a three-body problem. And three-body problems, that's a classification of problems, are dominated by chaotic elements. You can model them, but you can't comprehend them, essentially. They are beyond human comprehension. They exist in multidimensional space, and the more moving parts you have, the higher the dimensionality. It just unwinds very fast. It just comes completely unsolvable in multidimensional space. You just can't even touch it. Like millions of dimensions, you can't even touch it. The Earth system, it can be classified as in the realm of three-body problems. It is underpinned and dominated by chaotic elements. The chaotic nature of the Earth system. Okay, now I need to make a distinction. Chaos is used different with language. Okay, chaos, the word, is used differently by different people in different situations. One of the vernacular uses of chaos is simply things being disorganized. Things being disorganized. The room is chaotic. Look at all these toys and look at all these clothes. Let's straighten this up. Okay, that's one use of the word chaos. Another one is to give it kind of a diabolical element, that chaos is a force in the universe that is opposed to order. That order and chaos are in opposition. And that the solution is to get rid of disorder or chaos and let order reign and dominate and minimize chaos, because chaos is what? Evil, right? Chaos is evil. Order is good. Okay. That's a frequent use, frequently in economics and politics. And I've talked about those, and religion as well. I've talked about those on this channel just recently, that that politics, economics, and religion are abstractions. They don't exist. We invented them. That's why there's so many religions. That's why there's so many different forms of politics and how you organize people. That's why there's so much argument in economics and so many economical models and so much playing around with economics, right? These things are abstractions. We invented them, and they're not real. They're not even chaotic. They're just not real. They're completely unhinged from reality. They're useful, and a lot of things that are unhinged from reality are useful, right? A Stephen King novel or a movie based on a novel, right? These are useful. They get you to think about your life. They get you to think about, how people behave in situations, but they're fictions. They're just made up. Stephen King never experienced any of that stuff himself. He was never, he never experienced those horror situations. He just made those up. They're all in his head. And we kind of understand that. Yeah, he made it up. It's fiction. So it's no big deal. We understand he made it up. And maybe you like his fiction and maybe you don't. Maybe you don't like that genre of fiction at all. Maybe you like historical fictions, right? Alternatives to the U.S. Civil War, alternative outcomes to the Second World War, right? Those are fictions. Nazi Germany won. Japan got the bomb first. Those are all fictions. They didn't happen. We know what happened. It's in the past. We can just go look it up at Wikipedia. You'll figure out what happened if you don't know. And when someone writes about the Nazis getting the bomb and how that changed the second outcome of the Second World War, it's fun, it's interesting, but it's a fiction. It's made up. It's interesting to think about. Maybe you'll even learn something about technology and people and what people do and what motivates people. You'll read a fictional account of something and you'll come away from it, moved, educated, thoughtful. And fiction can do that. And our fictions, politics, economics, and religion are fictions that a lot of us live our lives by, are useful, but they're not real. They're not real. You think they're real, but they're not. And the reality, though, of the Earth system, unlike those fictions, and we create these fictions for ourselves because we're trying to impose order on the system, on the universe, on the Earth, on life, on all this variability, on the weather. We're trying to constantly impose order above chaos. We're trying to say, chaos, be gone. We're trying to impose order and predictability and trying to say that chaos isn't real. Go away. But it's exactly the opposite. Chaos is what's real. And we learned that in the 60s and the 70s, and it really blew people's minds away. And in this documentary, I was reminded of humans' antagonistic relationship with chaos. Why am I mentioning on this channel, which is devoted to global heating and climate change? Because the Earth dynamic system is dominated by chaotic elements. But science has an adversarial relationship with chaos. Scientists don't like chaos. Some of them for religious reasons. Some of them exactly the same way that Isaac Newton didn't like chaos or unpredictable results or results that don't follow a pattern or results that are amenable to mathematical attack. Okay? They just don't like it. They have an antagonistic relationship with chaos. And yet, here we are living on this planet with its hydrosphere and its atmosphere and its biosphere and its cryosphere and its lithosphere and its all the different components, all the layers of the onion, all of them geared together and interacting in strange ways that we haven't even been able to surface yet. And here we are on the Earth dynamic system, and it's dominated by chaos. And I don't mean chaos like you got to clean up your house or your backyard. I don't mean chaos as in opposition to order, and order is good and chaos is bad. I mean mathematical chaos, as was discovered in the 60s and the 70s. Let's see if I can find the right tab here. Yeah, The Essence of Chaos, Edward Lorenz. And this started the whole thing. This publication, his work, started the entire kerfuffle about chaos is real. And it's not spiritual, and it's not just a lack of organization, and it's not whatever, okay? It's real. It's there. It's always been there. It keeps cropping up in our science all the time. And we discount it at our peril, meaning our science becomes endangered. Our science. And why are we here? Why am I a scientist? Why do you care about science? We endanger our science and our ability to do science if we don't at least give some credibility to the underpinnings of chaos. Now, Lorenz was writing about the butterfly effect, and he wasn't writing about it. He included it sort of as a metaphor. And everyone misunderstands the butterfly effect. I don't care. It doesn't matter what people understand, but I'll explain it for you. Mathematical chaos. The understanding behind mathematical chaos is that initial conditions matter a lot. So if you have an experiment that you're not able to repeat, you add the ingredients, you stir them up, you heat them up, and you get a product that's never the same. Same ingredients, same amounts, same heating, same amount of duration, same container, everything is exactly the same. You just set up the experiments and you run them all at the same time. And every time they run, they get a different ingredient. Okay, that kind of That kind of chaos is what he was talking about. The initial conditions. You think you're setting up your experiments exactly the same. But the problem is, you can't. And when you're measuring out your ingredients, and you think you have 1 gram here, and 1 gram here, and 1 gram here, and 1 gram here, and it's 4 experiments, you're going to run them all at the same time, right? Yeah, sure, there may be 1 gram accurate to, 1/10 of a gram, or 100th of a gram, or 1,000th of a gram. But at some point, these measurements are going to be off by millions of atoms. Even if they're exactly the same, out to 10 decimal places, there's still going to be millions of atoms difference in the materials that go into the experimental conditions. And it turns out that's enough. That kind of a difference of thousands or maybe even millions of atoms different in the way you measured it and put them into the containers, or the way you heated it, and the temperature may have been off by, a thousandth of a degree when you heated it between the 4 experiments, a thousandth of a degree different. That's enough. Chaotic systems are extremely sensitive to initial conditions. And that's where we get the so-called butterfly effect. What he was trying to say with the butterfly effect is that you don't think of a butterfly flying through the air as creating a lot of randomness in the air, right? Here's the atmosphere. It's moving this way. It's moving that way. And then a butterfly comes through, and then now the air is moving differently. You wouldn't think that the movement of a butterfly's wings is going to change the atmospheric dynamics much. I mean, the atmosphere is 10 miles thick and it covers the entire Earth out to 25,000 miles at the equator. And a butterfly flying past me is going to somehow influence all that. Well, that's an initial condition. And the flapping of a butterfly as it passes in front of you changes the atmospheric component to some, 20 decimal points? But that's an initial condition. And so, somewhere nearby or far away, there could be a tornado spun up because, tornadoes are caused by chaotic elements. And so, in theory, the flapping of a butterfly's wings in Brazil, that disturbs the atmosphere enough that it causes a tornado in Kansas. That doesn't really happen, because there is so much other types of chaos. For example, a jet flying by overhead, right? That creates a lot more disturbance than the butterfly does. But he was trying to make a point. His point was that in chaotic systems, like the Earth dynamic system, initial settings, initial effects, tiny variations are enough to completely change the outcome. That's what a chaotic system is. And you can model them. Once again, like any other 3-body problem, you can model them, but you can't predict them. Those are 2 very different things. You can't predict what's going to cause a tornado. You can't even predict what's going to cause a thunderstorm. You can say, well, there's a chance of thunderstorms, but you can't predict when it's going to happen and where it's going to happen because it's underpinned by chaotic elements. And yes, a butterfly flapping down in central Kansas through a cornfield might cause a tornado, and that could be enough disturbance in the initial conditions to cause a chaotic event. I mean, in theory, that is true. I wouldn't think that the butterfly would, but something is going to. Something else chaotic in the system is going to come along and say, okay, that's it. We tipped you over the edge. And tipping over the edge, I want to see if I can find the right tab. Okay. I want you to look at this top picture. Let's see if I can bring this up. Maybe I can get a bigger version of this. I don't know. I should have stayed where I was. I'm going back. I'll go back to this picture. I want to point out to you there's a line here. It represents slopes. There's a valley on the left called, I've got my glasses, putting my glasses on, a metastable equilibrium. There's a valley on the right called a stable equilibrium. And there's a peak in the middle called an unstable equilibrium. And at each of those 3 points, there's a ball. The problem with chaotic systems is that if you can be in one of these valleys. If you're in a valley, if the ball has rolled into a valley, then it's probably going to stay there. And that's called an equilibrium. Equilibrium simply means equal. It's unlikely to be disturbed from where it wants to be in the bottom of that valley. It'll go left, it'll go right, but it'll come right back down because there's a slope. It's in a valley. The ball at the top that's on a peak is in what's called an unstable equilibrium. You can balance a ball on a curve if you're really careful. But if anything moves that ball left or right, it's going either right or it's going either left. And it does this catastrophically. So that's an unstable equilibrium. It can be an equilibrium, meaning it's not actually moving. But if anything happens to disturb it, it goes right or it goes left. And when it's on the slope, and that's the fourth ball, the one that's sort of in the middle on the angle, if it's in motion, then it's trying to attain equilibrium. It's on the move. It's going towards possibly another equilibrium. In all cases except the latter one, the non-equilibrium situation, in all three of those other situations, that ball might not be moving at all, and you say, it's stable. It's in a stable location, but it's not, because only two of those are stable, and one of them is unstable. And if you move the ball, and the middle one, when it's on the hill, it will go left or it will go right, and it will do so catastrophically, meaning you can't bring it back unless you apply another force. If you apply a force, then maybe you can put it right back on the top again, and that would be you with your fingers grabbing the ball and putting it back on the top. All right, but in energy systems or other types of systems, once it starts to move, it's gone. There really is no way to put it back. This also has another term called path dependency. So in the other two stable equilibria, there's the metastable and the stable. The metastable simply means it's not as stable as the other one. Okay, so you could force it out of the metastable state into the stable state with enough energy, but it would be harder to send it back the other way. So metastable is still stable, but it's not as stable as the point that's lower. So what did I want to say? So in energy systems or chaotic systems, you may be, well, in fact, probably you're always in either an unstable or a metastable equilibrium. And there's always something that's going to push you one way or the other. If you're in a metastable equilibrium, which is what the Earth system often is, then you're not going to see changes until something comes along to push really hard. But many parts of the Earth system are in unstable equilibria. They're ready to go. And right now, our planet, our Earth dynamic system, is being pushed very hard by global heating. And that's energy. And that can move the ball. We don't know if there are other metastable equilibria that we could go into, but we're about to find out. The place where we are now, the metastable equilibrium that we are in now, we have been in for about 10,000 years. During that time, we settled down, discovered agriculture, domesticated animals, domesticated fire. We discovered metallurgy. We traveled. Everything was stable. We could have stable ports, right? The sea level was neither rising nor falling. So we had stable ports of call. They became established. You could always go back. You always knew it was going to be there. You could navigate the oceans. You knew where the land was and where the land was not. And for the most part, it seemed pretty stable to us. But what it really was a metastable equilibrium. And if you were to push that system and get that ball moving, it might go into a very different equilibrium. And that's where we're headed now. For example, another equilibrium that the Earth system has been in the past and was in for a long time was ice-free. The current metastable equilibrium is being maintained by a very particular, very exact set of circumstances. Primarily, CO2 levels have been substantially lowered since millions of years ago. We are now reversing that. We are putting that CO2 back in the atmosphere. By doing that, we disrupt the equilibrium of the system. One result of doing that is that the system heats up. And so since the system is underpinned by chaotic elements, if you start kicking it around, then it's going to find a place where it can go over a barrier which in this case is in the middle of the diagram, it can go over that barrier and into another equilibrium. And the most likely equilibrium, the most likely one, based simply upon the history of the Earth itself, is ice-free. That's the most stable equilibrium. The Earth has been ice-free a lot. It certainly is in the last, I don't know, 100 million, 200 million years. The ice age that we've been in is about 5 million years long. And some people say even as little as 3 million. But for hundreds of millions of years, this planet was ice-free. There was also times in the past when this planet was completely covered in ice, snowball Earth. But once again, the conditions that gave rise to that and made that possible are gone now. And we haven't been snowball Earth for, I don't know, 500 million years, about that, maybe 600 million years. So the stable equilibria that are in our neighborhood right now, like these two valleys in this chart, are within each other's neighborhood, right? It can be either recurring ice ages driven by the Milankovitch cycles or no ice ages, even though the Milankovitch cycles are still there. So there might be some cooling, but there's no ice. So that seems to be the neighborhood that we're in right now. And we've spent most of our time as a planet, as if it's our planet. The planet has spent most of its time recently in the part of the neighborhood that is ice-free. And the difference seems to be CO2 levels, because the Milankovitch cycles have always been there. The Milankovitch cycles are orbital mechanics. So the Earth system has these stable or metastable, there's a stable equilibrium. They're all metastable, okay? The Earth system has these metastable equilibria that are all within the same neighborhood. And it doesn't take much to kick us from one to the other, all right? Because we definitely have had both now for hundreds of millions of years. We've had ice-free Earth and we've had ice-dominated Earth, including very huge glacial eras that, destroyed life over, I don't know, half the planet's land surface or more. And how you move from one part of the neighborhood to another is through chaotic interactions. So I was listening to this, last night, documentary. And this is another way to look at the same thing. A stable equilibrium is like a bottle that has water in it. It's heavy on the bottom. So if you tilt the bottle, it'll flip back upright. You tilt it, it flips back upright. There is a point where you can tilt it enough that it falls the other way, okay? So even though it's stable-ish. It's a metastable, all right? The unstable example here is a ballpoint pen, or in this case, a Sharpie, a wallboard marker. Something that's like, it's hard to balance. If you were to try to balance a ballpoint pen on its tip, maybe you could do it. But probably you have to futz around with it the whole time, right? If you ever let go of it, or if you ever bump the table, it'll just fall over, because that's an unstable equilibrium. Balancing a ballpoint pen on its tip, if you can even do it, is unstable. That's the reason why they're using a wallboard marker, because the tip is actually kind of flat. And then there's neutral equilibrium, where it doesn't really matter where you put the ball on the table. It's fine. Well, it's fine in the neighborhood of table. There's an unstable equilibrium at the edge of the table, where if the ball gets right on the edge, it'll go over. So even a tabletop with a ball on it isn't really neutral. I mean, in theory it is, but in fact it's not. If you hit the ball enough, it'll go to the edge and fall off, right? And then the next stable equilibrium, they're all metastable really. The next metastable equilibrium is the floor. And let's face it, if your house is shaking all the time, everything on your tables and your countertops ends up on the floor. And why is that? Because that's the most stable. The most stable part of your house is the floor. And the pictures and the tabletop and the countertops and this desk, all this stuff ends up on the floor in the case of an earthquake. Because these surfaces are metastable. They're stable enough, but they're really not stable. The more stable area is right here underneath the table. It's on the floor. And the Earth dynamic system is like that. We're kind of balancing right now. We have been for 10,000 years. We're balancing in a metastable state where when the Milankovitch cycle swung the other way, we would go into the next ice age. If this was only metastable, this was not stable. Although people have pointed out that our current climate regime has been metastable for a really long time. They look back in the geologic record and they don't see interglacial periods like what we're going through right now. And people have even said, yeah, this is a really unusually stable interglacial period. And I'll tell you right now, I think it's because of humans. I think we've gotten enough technology together that this time when we went into an interglacial, we began to dominate the Earth system by clearing forests and draining swamps and building huge cities and cutting down trees and setting them on fire. And then, of course, eventually discovering iron ore and smelting iron and making charcoal and cutting down more forests. And then eventually discovering, coal, discovering fossil fuels in general. And, we've just been changing the system, driving it further and further and further away from the next ice age. Even though the Milankovitch cycles are already swinging in that direction, swinging towards, ice dominance, we're very busy going the opposite direction, heating the planet, heating the planet, heating the planet. And between the two driving forces, the swing of the Milankovitch cycles and also our activities, between those two drivers, we're actually heating the planet. We're actually probably going to make it ice-free. And at that point, the planet will be more like it was 50 million years ago, when there was no ice. And that's another metastable equilibrium. This planet has been mostly without ice. There's no reason for us to expect this planet to have ice. There's no good reason. The only reason is because the CO2 levels in the atmosphere have been so low over geologic time. And that's too bad, because we're changing that now. We're changing that now. We're up to 420 some odd parts per million. Historically, during an interglacial, it might get up to 280. During an interglacial, well, we're in an interglacial right now. And maybe there would be, 280 or so, but it's not. It's 420. That's us. We did that. We did that. We've been doing that for 10,000 years. We've been driving that for 10,000 years. See some of my previous videos. I should link it, but I'm too lazy, so I'm not going to do that. Well, I might. We'll see. Where I discuss that. Okay. Scientists do not have a working relationship with any of this. We're happy to model the climate system, but we can't predict it. We're happy to model it. That's all we've got, is modeling it. The Earth dynamic system is basically a three-body system, except it's not three bodies. It's thousands of bodies, and they're all geared and orbiting around each other. And the problem, the phase space for predicting, not modeling, but predicting the Earth dynamic system is probably millions of variables, millions of dimensions. And there's no way. We can't do it. So we run models instead. People say, the models have lots of problems. Yeah, but that's all we got. Oh, and models aren't too bad. I mean, models put men on the moon. Models put spacecraft on Mars. Models, able to put spacecraft in orbit around Mars and to visit the moons of Jupiter and Saturn. So, I mean, the models aren't too bad. We know how to run models. Our climate models are getting better all the time. But that's all we've got as models. You'll never have a predictive science for global climate because we don't really understand how the system works. It's a multi-body problem. It's way past three bodies. And even our best thinkers gave up on the three-body problem. The three-body problem is completely baloney. Let me see if I can look up here. Let's see, what's it called? A triple pendulum. I can't spell this morning. Pendulum. Triple pendulum. Okay. The triple pendulum. This is a YouTube video. This one's probably okay. The triple pendulum. Let's see if this even works on OBS, my software here. Okay. This is a triple pendulum. See those discs? It's like a three-body problem. Now, you see, there is a pattern. You'll notice there's a pattern. But what you don't understand is there can't be a pattern. This cannot be predictable. It's underpinned by chaotic elements. And eventually, of course, it'll stop swinging. I mean, that's just because of friction. But the problem with these pendulum is that even though your mind can create a pattern, the truth is there isn't one. And that's what Lorenz discovered with his, where was it? This one. This is a chaotic pattern. Now you'll see there's kind of a pattern here. I mean, there's places where it swings. There's places where it doesn't swing. There's kind of a shape to it. You could even, say, oh, it's like a bird's beak, and there's a bird head here, and this is the bird pattern. But it isn't. There is no pattern. There's a phase space. And if you were to swing the pendulum for this particular chaotic space, there would be no way. There'd be no way you'd know how this thing works out. It's a space. But the point where you are in that space is completely unpredictable. It cannot be predicted. It can be modeled, and that's what this particular three-body pendulum is doing. It's running a model. It's an analog model. It's not a computational model. But you could do this with computations. You could model this. And in video games, they do that kind of thing all the time. In video games, they have what's called game physics, in-game physics. They model behaviors like ricochets and things bouncing off of each other, and light entering through a aperture and bouncing off of things and casting shadows. That's all modeling, right? It's chaotic. And especially when things are moving relative to each other, it's chaotic, but you can model it just fine. And this triple pendulum is a chaotic system. It has patterns, but it's not predictable. It's just not. You could watch this for an hour, and there's no way it's ever going to repeat itself. Now, the three bodies move inside of a phase space. So none of these three bodies will ever be off the screen, for example. They're physically tied to each other, and there's a space in which they orbit. It's a little circle, right? But where each body is in that circle cannot be predicted. It is a chaotic system. This is a chaotic pendulum. That's what it's called. And you can never predict where it's going to be, but you can model it. But even your model is heavily dependent on initial conditions. So wherever he starts this thing, you're going to get a completely different traceable phase space, completely different. And you can never start it exactly the same. You can't. It will always be different. Every single time you run this pendulum, it will always be different, because the initial conditions have to be completely, absolutely exact. Now, you can do that in a computer. You can set all the initial variables to 0, and you can do that in a computer, but you can't do that in a physical thing. And when you set this pendulum moving, it doesn't matter how you set it up in initial conditions, it becomes almost immediately chaotic. And that's how the Earth dynamic system is. We are messing around right now with the conditions of the Earth dynamic system. It's in one of these metastable equilibria, but it can be pushed out into a different one, and then we're screwed. Then we're in big trouble, because that's not where we evolved. That's not where we belong. Now, scientists have an antagonistic relationship with chaos like this. They have an antagonistic relationship with this kind of thing. Yeah, there's a phase space, and it has a shape. And this, by the way, this diagram is multidimensional. There's a shape in multidimensional space, and you'll be in that multidimensional space probably most of the time. But where you are in this space is completely unpredictable, because it is chaotic. We are monkeying around, literally monkeying around. We have no idea what we're doing. We are poking sticks at a system that is like this. That is a phase space of chaotic equilibrium. And the equilibrium we've been in for 10,000 years is only one of billions, an infinite number of equilibria that this planet could be in. And the next set are unpredictable. We can model it, but our models are inadequate. But regardless, what you have to understand is it's unpredictable. You're monkeying with a system that exists in phase space. That's the reality that's the lesson of system chaotics. You're fucking around with a system that is in a metastable equilibrium in a huge phase space. And one of those phase spaces we know for a fact, and we know probably dominant, is ice-free. And being ice-free is the end of the human world. I don't know. I say the human world. It's not the end of the world, because the rock is going to be fine. The forest will be fine. The animals will be fine. They'll be fine without us. We won't have the human world. And you are dependent on the human world. And your human habitat your cities and your aircraft and your food and your agriculture and your food deliveries and your food processing and your water and your heating and your cooling, all that human habitat could only exist in this particular interglacial period. And we've been monkeying around with it, poking sticks at it, fucking around with it. And we're going to leave this space. We are leaving this space right now. We are going to leave this space that we're in right now, that we've been in for 10,000 years. It's been oh so stable. Wow, what a mystery. Why is this interglacial so stable? I don't know. Maybe someone's been screwing around with it. Maybe someone's been pushing it in a particular direction. And maybe that someone was us. Yes, exactly. And you can't, I got to sign off. My wife just got home. You can't expect scientists to ever talk about this. Only someone like me will talk about this because I don't have grants. I don't have tenure. I don't have papers to publish. Okay. And scientists doing work in climate studies and, Earth system dynamics, they don't want to talk about this picture. Somewhere, we are in this picture somewhere. This is a picture of a phase space that is unstable, that is chaotic, that is dominated by chaotic forces and elements and behaviors. And we are somewhere in this phase space. And everywhere else, there's an infinite number of other places we could be. And will we like those places? Will we like the world next that comes up? What about the ice-free world? Is that going to be cool? What about a world that's dominated by hypercanes and massive rainfall events? Is that going to be okay? What about a world that's nothing but one huge, dense rainforest that you can only fight with nuclear weapons? Is that going to be okay for us? Clear-cutting forests with nuclear weapons so we have a place to live? Is that going to be okay? You looking forward to that? Because those are other stable equilibria. And the one we're in right now just happens to be the one we're in. It just happens to be the one where we evolved. It just happens to be where we discovered agriculture and fire and metallurgy and went to the moon. The one we're in now has allowed all that to happen. What about the next one? What about the next metastable equilibrium where we are rapidly going? The Earth is on an excursion, as I like to say. It's actually a term borrowed from nuclear power. When a nuclear power plant becomes unstable, again, we're using the same terms here, okay? When a nuclear power plant becomes chaotic, then they say it's on an excursion, all right? And our civilization, the planet as it currently is, the Earth dynamic system, is on an excursion. And we did that. We did that. We made the system unstable. It was already metastable, but we've pushed it so much that now it has to go somewhere else to become stable again. And because the path dependencies, which is another part of this chaos discussion, because of path dependencies, we can never really return to this. You could actually, if you could, I mean, now we're violating the laws of physics, but if you could somehow remove the CO2 and cool the planet, would we come back to where we are now? No guarantee, because of path dependency. We don't necessarily retrace the path that brought us here in the first place. We retrace a different path. As we retrace a different path on the way back to this, we may end up someplace else. The places that are arable land now may not be. The places that are deserts now may become arable land. The rainforests may be gone. Maybe they become deciduous forests. Maybe they become savanna. It'll be a different world. The world will change because of the path dependencies of how we got to this world in the first place. And this is all chaos. This is all mathematical chaos. This is all chaos theory. All of this is chaos theory, which we discovered, quote unquote. I mean, it was always there. We discovered it. We had to finally come to terms with it in the 60s and the 70s, and we never did. Most scientists have an antagonistic relationship with this. And you're going to have to go where they take you. The scientists are going to help you navigate the coming excursion, and they have an antagonistic relationship with chaos. That means they have an antagonistic relationship, a non-working relationship with the underpinnings of the Earth dynamic system. And, my theory is that people are going to fall back to abstractions. When they finally understand that the Earth is actually dominated by chaotic elements, then they're going to go back to their prior relationships with chaos. That it's order versus chaos. We must fight chaos. And I got to tell you, just like I did in the last video, I think it was, chaos is often attributed to evil influences. Now we're getting into religion, right? Abstractions. evil influences. Are those real? Did the dinosaurs call the Chicxulub meteorite evil? Of course not. It was just a phenomenon of nature. But we attribute goodness to order and evil to chaos. And one of the ways we handled chaos in the past, real chaos, not chaos like your room is a mess, real chaos, elemental chaos, was by killing people. We would find someone to blame. If our village had a bad harvest and that seemed chaotic, like the last 3 years were great and this year was bad, then someone's to blame for that. Someone insulted the gods. Someone insulted the land. Someone did something bad. Someone cursed us. Someone worked witchcraft against us. And then they go out looking for witches. And of course, you can always find witches if you want to. And you make them suffer and you torture them until they confess, and they name other witches, and pretty soon you're rounding up all the people in the village and they're all getting interrogated and tortured, and pretty soon half the village is hanging from oak trees. Because in an abstract environment, in an abstract worldview, we saw order and predictability as sacred and chaos as evil. The earth is dominated by chaotic elements. We still have an antagonistic relationship with that. We will not save ourselves. We won't. We will resist the chaos as if it were evil, as if it were counter to our best interests. It is the system in which you are embedded. It is the earth dynamic system. It is inherently chaotic. It is dominated by chaotic elements. And we're about to find that out. Now, we won't find that out. We will never understand that. I'll understand it. I see what's happening. I know exactly what's happening. We are a dot somewhere in this diagram. And there are an infinite number of dots just waiting for us to go there. And we're going to go there. We're going to visit phase space. We're going to travel through this multidimensional phase space until we find our next metastable equilibrium. And my guess is, based on past geological realities, it's going to be ice-free. And it'll probably stay ice-free for tens or hundreds of millions of years until some path dependency gets us back on the path of interglacials, glacial epochs and interglacials, which is where our civilization arose during an interglacial. A very, very small and peculiar slice of history, Earth's history. These interglacials are very, very limited, very tiny, but they happen to be where humans evolved. 300 million years of physical and cultural evolution during ice ages. There have been ice ages for as long as there have been humans on Earth, derived from the primates. And that's us. And that's going away now. And where is there any room on this Earth for us when we have migrated this planet to another phase space, a different part of phase space, a different metastable equilibrium, more like when the dinosaurs were here, more like when the Earth was probably, covered in rainforests and covered in swamps, and there was no ice anywhere on the planet. Is there anywhere on Earth for us in that situation? Probably. But will it look like this? Will we have internet and satellites and rocket launches? I don't know. Maybe. I think at the very least you'll be living in villages. Small numbers of people, villages a little distance apart because you need the resources, and maybe there'll be 1/10 of 1% of the current population living in villages, living off the land and the resources around them, and maybe traveling to the next village is a 2-day event for you. And no one does that. And we just live in our villages and we travel seldom and only for special reasons. And, and most of the world is populated with wild animals living in forests and jungles like it used to be. That's the next metastable equilibrium after we melt all the ice and raise the temperature of the Earth by 10 degrees C, 20 degrees Fahrenheit. Yeah, that's the next place for us, is hothouse Earth. And rainfall and hypercanes and jungles. We can't predict it, but we can model it. Will they? I don't know. Science has an antagonistic relationship with all of this. All of it. I don't know. I don't know what we're going to do. We need to stop burning fossil fuels with immediate effect. We need to throw the brakes on this thing. Are we going to do that? No. But that's what we need to do. I mean, I say I don't know what to do. I know what we need to do. We need to stop burning fossil fuels with immediate effect and take our hit. And I know that means a lot of people won't be able to live because a lot of them are getting their food from fossil fuel-based agriculture and fossil fuel-based communications and fossil fuel-based transportation and fossil fuel-based food production and fossil fuel-based markets and cities and everything else. I understand that. I understand that civilization lives, breathes, runs, swims in fossil fuels. I understand that. But you can't have them. So you're going to lose your civilization. But you can't have that either. We must stop burning fossil fuels with immediate effect. And I think the only way that people survive is they come together and they form villages. And they become mutually dependent on each other. And they bring in the crops together and they process the foods together and they raise their children together and they take care of each other together. And they fight off the abuses of nature together. I think that happens. I don't think we continue as a species without that happening. And really, we're okay with that as a rule. But that's what you have to do to fight chaos. And the system is chaotic. And you simply have to accept that. And it's not a good versus evil or right versus wrong. It's just the way the system is. Get used to it, Sparky. That's your future. System chaos. We've known this for a long time. We've known this for a long time. We just refuse to believe it. We still refuse to believe it. And I think we're going to go right into the jaws of disaster, never understanding what hit us.